What's outside the universe? My friend Melody asked me this question when I was 8 years old. I usually had good answers for science questions. I was sort of a library guy, but this time I had no idea what to say. The question was scary. I grew up in southern Utah, in the western part of the United States, and this is the home of red rocks, hot, dry summer nights, and clear skies, and these are perfect conditions for stargazing. And as a kid, Melody and I would often bicycle out of town to get away from the lights of the city, and we would look up at the sky and we would ask each other questions about the universe. How big is the Earth? What is the sun made of? Why can't I see a black hole? How far away is that galaxy there? What's at the edge of the universe? When she asked me that one, I stopped and I thought about it. And finally I said, I don't know. And Melody said, my ancestors thought that the Earth was a big flat rock with a solid dome of sky above it. The stars were painted on it. And it was all held in the hand of a big creature who would occasionally shake it. And we stared up at this dome of stars. And I said, well, I think that's a first good guess because they didn't have telescopes back then. But now that we know that the universe is huge, I don't know what's at the edge of the universe. Melody was an indigenous Native American from a local tribe. I don't remember if she was Paiute or Navajo, and the other kids at school would sometimes make fun of Melody and calling her nasty names. She didn't like tests, she didn't like homework assignments, but she ran circles around the other kids in classroom discussions with the teacher, and there was a reason why she and I were friends, because Melody was never afraid to ask the big questions. And when she finally said, what's outside the universe? The question caught me off guard. Well, nothing. The universe is everything, so it doesn't make any sense to ask what's outside of everything. Everything is everything. Yeah, but if the universe has an edge, then there must be something beyond that edge, she said. And we stared at the sky for a very long time. And finally I said, maybe there is no edge and no outside. And Melody said, yeah, maybe the universe just goes on forever and ever, and that's all there is. And again, after a long pause, staring at the sky, I finally said, everything is terrifying. And as you can see, I was an extremely serious child. Maybe not so completely serious, because to me, terrifying doesn't have to be a bad thing necessarily. But before we go too far, we need to answer one very important question. What is the universe? Picture the last time you were out in the wilderness and you stared up at the night sky. Thousands of pinpoints of light, photons from galaxies and stars, thousands of light years away, a light year being the distance that light travels in 1 year, to finally reach Earth and smack into the back of your retinas. When you look up at the night sky, you're looking backward in time, but look closer. In between those points of light, what do you see? It looks like empty space, but it's not. Your eyes are pretty good photon detectors for one particular type of photon, but on cosmic scales, your eyes are terrible experimental apparatuses because they can only see a relatively narrow range of photon wavelengths, and there's so much more hitting the Earth than what we can see with our eyes. If you were to use humanity's best photon detectors, like satellite telescopes, you'd see hidden light, photons from galaxies millions and billions of light years away, and eventually you'd see something absolutely remarkable: the cosmic microwave background radiation, light from when the universe was only a few 100,000 years old. This is the closest we can get to a baby picture of our universe. But wait a minute, baby picture, a few 100,000 years old? That's a pretty old baby. Where's the light from before then? Most of that light hasn't had time to reach us yet and never will. All of those galaxies we see up in the space, in the sky, they're all moving apart from each other in every direction because the universe is expanding. But expanding into what? Is our universe like a balloon put into a box and then the balloon is inflated and the balloon is then expanding into the box? No. Space itself, the background metric spatial grid upon which everything rests, is being stretched. Two galaxies in our universe are like two pins stuck into a rubber sheet that is being pulled in all directions. From the perspective of the ant on the sheet, nothing happened to make the pins move. Space itself, the sheet, is being stretched, and the distance between them is increasing. And as you know, if this is true, we can run the clock backwards, figuratively. And it means that at one point, far, far long ago, 13.8 billion years ago, everything in the universe had to have been packed into a tiny little dense point that then started expanding. And this, as you know, is the concept of the Big Bang. So the universe is expanding, but it's not just the fact that our universe is expanding, but the particular way that it did so throughout its history. There's so much that we can't explain if our universe always expanded at a normal, boring, slow rate, constant rate, its entire history. Why do we see big things in the universe at all, like galaxies or cosmic structures? Why does the stuff in that part of the sky look more or less like the stuff in that part of the sky? Why is this cosmic microwave background radiation, the baby picture of the universe, essentially uniform in temperature? Don't let the color coding fool you. Those colors were put there by my astrophysics colleagues to show the variations, but it's basically uniform. None of this makes any sense unless, at the moment of the universe's expansion in the Big Bang, it didn't just expand at a constant rate, but instead first insanely inflated before then tapering off to a much more gradual rate. And this inflation wasn't some minor thing. Imagine if we took a horse and magically inflated it to the size of the current observable universe in 10 to the minus 32 seconds. That's what inflation was like at the moment of the Big Bang. This inflation happened much faster than the speed of light. And as you know, the only way that we here on Earth know that anything exists in space, in the universe, is if we receive a signal from it. And the fastest that any signal can possibly be sent is light speed. Thus, if this inflation happened faster than the speed of light, most of the universe was instantly separated from us forever and always will be. Thus, we are left with a new concept, the observable universe, which is of small volume, defined by all of the stuff that could ever possibly send us a light signal that could ever possibly reach us, which must be a tiny subset of the entire universe, within which there have to be a large number of other observable universes for, in principle, other observers. And it gets worse. If you look closely at the mathematics behind this idea of the absurd inflation of the fabric of space, it should go on forever, infinitely. But in our universe, it didn't. It tapered off and has been going at a much more gradual rate for billions of years. This means that our universe and the fabric of space on which it sits can be thought of as two different things, because our universe is a tiny pocket, almost a bubble, that was snapped into existence when this fabric of space inflated. And this inflation goes on forever, infinitely. And with infinity, you know, if it happens once, it happens again and again and again. This means that our universe doesn't have to be the only bubble that popped up from this inflation of the fabric of space. And in fact, if it's infinite, there must be an almost infinite number of other universes that were also popped into existence by this inflation of the fabric of space. In most of these universes, the constants of nature were probably something totally different, and they're completely boring and empty voids, and maybe inflation never slowed down like us, and you wouldn't want to live there. But with infinity, there must be other universes like ours. In one of them, one of you wore different socks here today. In another one, coffee is pink. And in another one, an asteroid obliterated an Earth-like planet just as protozoans were starting to evolve. If our understanding of the inflation of the fabric of space is correct, then this isn't just wild speculation, but necessary due to infinity. But I see the looks on your faces, and you should absolutely be skeptical at me because, hey man, you're a scientist. Where's the evidence for this? And you're absolutely right. So it turns out that this is, of course, just circumstantial at the moment, right? We have no direct evidence that this is true. However, it turns out that this is not the only piece of circumstantial evidence that we have that we might live in a multiverse. Our universe seems to be filled with magic numbers, constants of nature that we just measure, but have no particular explanation for what they are. And as a physicist, I hate it when I see something without an explanation. I want to know why that's there. For example, my colleagues and I at the Large Hadron Collider at CERN in 2012, we discovered a particle called the Higgs Boson particle. And this particle is a very weird and important particle. A reminder. The Large Hadron Collider is a 27-kilometer circular tunnel on the border of France and Switzerland, 100 meters underground. And in this tunnel, we use superconducting magnets colder than outer space to accelerate protons, you're made of protons, to almost the speed of light. And then we slam them into each other millions of times per second. And we do this for weeks and months and years, and we build up the largest unique data set in history that is a record of us recreating the conditions of the universe as they were just a fraction of a second after the Big Bang 13.8 billion years ago. We'll let this collision happen. Pow. It's beautiful. And in 2012, when we discovered this particle called the Higgs Boson particle, there was a fantastic celebration, and there was champagne, and then 2 white males won the Nobel Prize. What else is new? But there was also a lot of head scratching, too, because honestly, we probably shouldn't have found this particle at all. The largeness of experiments like the Large Hadron Collider is important because bigger machines correspond to higher collision energies. And thanks to Einstein's famous equation, E equals mc squared, there's an equivalence between energy and particle mass. And if nature has a particle with a mass m that's all the way up here, we need to keep building bigger and bigger colliders to hope to find this particle. And when we finally found this particle at the Large Hadron Collider, it made us start to think some weird things, because in our very good model, our very good theory of everything that happens at the smallest possible scales, there's nothing to prevent the Higgs boson mass, that m, from being something gigantically high, way outside of the range of the Large Hadron Collider. But we found it down here. This is hard to explain, because if the value of the Higgs boson mass was something a little bit different than what it is now, our universe would be a very different place. The Higgs boson is not the most important thing. The Higgs boson is an indication, proof positive, that something called the Higgs field exists. And the Higgs field is kind of like an invisible jelly that permeates all of space everywhere. And it's the thing that allows your particles to even have masses at all. And if there were no masses in your particles, atoms would never have formed in the early universe, and you and I would not be here to have this conversation today. So it's a good thing that the Higgs field exists. It's good that the Higgs boson exists. But what's keeping the Higgs boson mass down here? It's almost as if there's some weird quantum mechanical shelf that's holding the Higgs boson mass up here. And in a particle physics sense, this would correspond to a few extra particles through some complicated interactions help regulate what the Higgs mass is. That would be great if we found these. It would explain wonderful things about our universe, and we'd be very satisfied, and physicists everywhere would go, ah. We do not see these particles at the Large Hadron Collider. Why is the Higgs boson mass what it is? Did we just get lucky? Maybe it is just luck, but a particular type of luck. Our universe loves statistical distributions. If you hear a nerdier statement in the next 2 days, tell me and I will fight that person. For example, the average resting heart rate of everyone in this room will be distributed as some kind of a Gaussian. If you stand on a street corner, the rate with which cars will pass you is distributed as some kind of Poisson distribution. In a sense, statistics and math seem to transcend our universe. So what if our Higgs boson mass is just one of a possibly infinite number of Higgs boson masses in a multiverse? In our universe, the Higgs boson mass was just right for atoms to form and for you and I to be here right now, but in almost all these other ones, it was some completely different value, and they're completely empty voids, and again, you wouldn't want to live there. The lack of these extra particles, this shelf at the Large Hadron Collider, is not proof positive that we live in a multiverse, but it's another piece of circumstantial evidence that we should take seriously this concept. But again, I see the looks on your faces, and you're absolutely right to be skeptical. It's totally okay to yell at the experimentalist, "You're an experimentalist, man. How are you going to test this?" I like the way you think. And it turns out there are some ways we might be able to test this, but they're either extremely difficult right now or face some rather large technological challenges. But one way would be to look for a bruise on our universe. Remember that almost infinite number of other universes that popped into existence when the universe, the fabric of space inflated right at the moment of the Big Bang? What if two of them inflated or expanded right next to each other and bumped into each other? Could that be what this little cold spot is in the cosmic microwave background radiation? The jury is still out as to whether this hypothesis fits this data better than some other hypothesis, but this is an active area of investigation. Another way is a way that you could look for new undiscovered particles at extremely high masses, so you have to build bigger machines, AKA my day job. So there are plans right now to build the next generation of particle physics collider that would be something like 100 kilometers around. It would reach energies something like 7 times what we can right now, which would open up completely uncharted experimental territory. That would be amazing. And if we don't see these new particles, these extra particles at this machine, would that satisfy me? Would then I be able to come back to next 20 and say, or whatever, next 70 or something like that, and come back and say, yes, we now live in a multiverse? No, that's not enough. We need to go higher to rule out all possible energy ranges and mass ranges. What if we were to build a particle collider around the outer edge, around the circumference of the moon? This seems like a crazy idea, but think about all the action and the activity right now, the desire of these private companies, and there's so many people that want to go back to the moon, either to set up a base or to do some mining, which I think we should prevent, and we should also they want to set up a colony, even though I hate that language. All this interest in going back to the moon, why don't we set up some gigantic science experiment instead? And I don't have time to go through all the things that someone in this room would have to innovate to make this possible. Imagine what you and your company could do if we got this machine off the ground. But what if? But would that satisfy me? And would that satisfy me finally, if we built the moon collider and I was like 300 years old and I was able to stand up at NEXT 2400 or something like that and say, yes, in my old, biblical voice, we live in a multiverse because we didn't find these extra particles at the moon. No, that's not enough. To really do it right, to go to the ultimate highest energy that makes any sense in particle physics and quantum mechanics, we need to reach something called the Planck Scale. And at this point, this is an energy range that's so high and so definitive that we'll be able to understand everything about our universe. We would understand everything about dark matter, dark energy, what happens inside of a black hole, why gravity is so weak compared to the other forces of nature. We would understand all of this. But to reach the Planck energy, we would need to build a Large Hadron Collider style collider that circles around the outer edge of the solar system. Clearly, we're going to need some major innovation to make this one happen, but Luckily, we're at NEXT19, where I can't seem to walk 3 meters without meeting some world-changing innovator or someone who aspires to be one. So catch me afterwards, and we'll brainstorm ways to make this happen. But when we build the ultimate Hadron Collider, and we will, what will we do with the answers that we get from it? Even if we were to build this, and if we were to not find these extra particles at the Large Hadron Collider, this still would not be definitive proof that we live in a multiverse. I currently have no idea, science currently has no idea how to define what we'd even do to communicate with another universe. Such a concept currently makes no sense. So, are such questions meaningless? You may say yes. And in fact, some scientists would agree with you. And in fact, some scientists even attack our attempts to learn more about such questions by building bigger colliders, saying that such questions are non-scientific. But is that true? We started from known science, observations of the world around us, and we followed the chain of logic to arrive at the startling conclusion that yes, we may in fact live in a multiverse. It's very bizarre, but it's clearly science. Just because we can't answer the question now doesn't mean that we never will. And something like a moon collider, for example, is just regular impossible. It's not impossible, it's regular impossible. And regular impossible we can do. Regular impossible is just impossible right up until the moment someone makes it possible. But why do people object to questions like, what's outside the universe? Is it because they could be afraid of the answer? And is this the same fear that led people in the past to object to other questions, similar questions like, is the Earth really at the center of the solar system? Or are the stars painted on a solid dome a few kilometers above our heads? The fear that you and I are not as special as we think we are. And what if I were to tell you in this room, that there is a parallel universe out there somewhere where you already found the courage to inspire your team to take your project or your company to the next level, and you did it last year? What if I were to tell you that there is a parallel universe out there somewhere where you already put the right resources toward developing that technology you wanted to do for a while, and your company broke into 3 new markets last quarter? What if I were to tell you there is a parallel universe out there where you finally made that call that you've been hesitating making to that long shot contact, and they said yes to a collaboration? What if I were to tell you that there is a parallel universe out there somewhere where you already quit your current safe job that you don't like so much, and instead you're right now with a team of awesome people working on that gigantic thing that you've been thinking about for years, like starting a humanitarian organization, or figuring out a way to solve wealth inequality, or figuring out a way to, use blockchain technology to prevent governments from secretly surveilling their citizens, something. What if I told you that there is a parallel universe out there where my colleagues and I have already figured out a way to accelerate particles to much higher energies in a smaller amount of space? That'd be great. Research is going on right now for something called plasma wake-field technology that promises to revolutionize particle physics. We probably won't need eventually the solar system collider, as cool as that would be. What if you were to join this effort? I don't work on this, so it's not like it's an advertisement. What if you were to join this effort, to join with some of the brightest minds on Earth, to work toward revolutionizing our understanding of nature? Going through thought processes like this and the thought experiment is in fact fascinating. But at the end of the day, again, this is all speculation. We have absolutely none, zero direct evidence that we live in a multiverse. And this idea that there could be some parallel universe out there with a different version of you doing different things, perhaps better things, that may be a comforting fantasy, but it's something that it's entirely possible that we'll have, it's physically impossible for us to ever have evidence for this concretely. I have no idea whether we live in a multiverse. And that, the fact that we have this one universe here, the fact that this is just a fantastic kind of fun, let's laugh about it type thing, this thought experiment, this makes it much, much more important that we all right now get to work right here in this universe to make this universe the best one that we know how to construct. Because at the end of the day, I can't tell you whether we live in a multiverse, but I can tell you this for sure. What you know right now, what your experiences are right now, is not all there is to know. And to know more, you have to stretch yourself. You have to push beyond. And to me, the safety of ignorance will never compete with the scary beauty and terrifying joy of knowledge. Always ask the big question. Always allow yourself the bravery of stepping into the unknown, and always seek out new knowledge to vanquish the fear. Because you know what? This fear, similar fears that people had in the past, people will have in the future, this fear that we have keeps us from recognizing some of the most essential, fundamental realities of physical objective reality. We don't need to be afraid of an almost infinite number of universes, because at the end of the day, we know one thing for sure. There is at least one universe. And when you and I, humans, ask questions about our universe, small ones, big ones, we, humans, are the method by which the universe asks questions about itself. And when I see the government of the United States putting literal children into literal cages on the border of United States and Mexico, and when I see how otherwise intelligent people are being suckered into voting for racist, xenophobic, misogynistic, white nationalist parties all over Europe, and when I see how we've allowed decades of unfettered global capitalism to destroy the climate and we're not acting fast enough to fix it, and when I think about my friend Melody and how the other kids at school would make fun of her, and how that made it difficult for her to go to class, and how she never went to high school and dropped out, I feel anger. But it's not just regular anger. Oh, I feel regular anger too, but as a physicist, I feel an extra layer of anger, because when we allow such things to happen, we're betraying this cosmic truth that you and I are all parts of the same universe, and we're all in this universe together. And so back on those red rocks, when I was 8 years old, I said to Melody, everything is terrifying. And she said, yeah, it's scary, but it would be scarier if I were out here by myself. And I thought about it for a long time, and I looked up at the sky, and I finally looked at her, and I said, yeah. And we both looked up at this dome of stars, the stars and galaxies watching us from very far away. Thank you. Woo.
Yeah. Thank you very much. Thank you.
Thank you. Thank you. Thank you. Thank you.
Yeah.
Thank you.